Now let's see how we can improve the baseline cycle gain using some techniques. As mentioned, we use the edge smoothing using a script, and I save the smooth cartoon images to a new directory. For perceptual loss, we need actually the content loss and the style loss, which is very similar to the approach we used in neural style transfer. We need to extract the content and style features from the pre-trained VGG19 model, and we want to minimize the difference between the two cartoon images and generated images measured by these extracted features. Same as in neural style transfer, I also added the Gramian matrix conversion for the style feature comparison. Note that we in here it's a little different. I added both content and style loss to the same generators, which is different than in neural style transfer. With the careful customization of a CycleGAN class, we can simply provide a content style loss function as an additional option to the CycleGAN compiling method to improve the baseline model. And below you can see the training step summaries, which is customized from the comments in the Colab mentioned in the tutorial. The first step is pass image, a real image through the generators and get the output, and pass the generated image back to the generator, check if we can predict the original image from the generated image, and then do an identity mapping for the real image. And the fourth step is the pass the generated image in step 1 to the corresponding discriminator, and fifth will be combining 3 loss functions to a total generated loss. And sixth step is the optional one we added. So basically, if the content loss function is provided, we will add content loss and style loss to the total loss. And seventh step is basically calculate the loss for discriminator, and then we update the weight of the generator and discriminator. And that very last step, we return the loss for losses in the dictionary. Regarding training epochs, we basically take the same one from the tutorial, which is 19, just for consistency and for comparison purpose. For tuning, actually I didn't have much time to tune the hyperparameters extensively. In here I set the hyperparameters so that the loss function from the content and style features are comparable to the in the scale to the baseline generated loss values. And then we can see the results. Okay, so here you can see the training history from the generative side. I think in general, after 20 epochs, both models fail to reduce the generator's loss, but fail to reduce the loss by much further. So we can start with a smaller number of epochs when enhancing the model in the future. 90 epochs seems to be a little bit too much, but that's the one picked from the tutorial. We can also use the early stopping in the future, but we have 4 loss functions, 2 for generators and 2 for discriminators. So that could be a little tricky. On the other hand, the models could stuck at a local minimal that we are not aware of. So based on the paper of Cartoongan, actually, if we pre-train generators, that should help this situation. We can try that later. So now let's take a look at the cartoonization quality on test set. Here I generated cartoons based on 8 test images so that we can eyeball the qualities. The cartoon generation are done by only one code, basically take the prediction by calling the generators function of the CycleGAN model. So below you can see the original image in the second column, the baseline CycleGAN generated image, and the third column is the improved CycleGAN generated image. We can observe that it's easy to notice that the color scheme of the generated image are very close to the Simpsons cartoon. We can also see the duck style mouse features from the Simpsons are generated in the images. All generated images preserve the basic patterns of the original real people photos, which should thank to the cycle consistency loss function. On the other hand, the output of the improved CycleGAN doesn't seem clearly better than the baseline model. In general, the improved CycleGAN creates the image less weird, while the baseline CycleGAN creates images more like monsters instead of cartoons. By eyeballing, I think neither model creates image very closely to the Simpson-style cartoon images. So, in a nutshell, CycleGAN did an acceptable job in cartoonization translation, but the results are not great. The improved variant doesn't seem to translate the images much better than the baseline model. Here you can see the image for more examples. And this is the duck style mouse. Okay, as a conclusion, using CycleGAN and its variant, we explored converting real photos into cartoons. Both baseline and improved models show some promise but perform better in retaining the information from the input than translating to cartoon styles. So incorporating the techniques from cartoon GANs, which is basically edge smoothing and perceptual loss, proves some interesting usage but not really significant improvement. While these models show some potential, further tuning and exploration in the hyperparameter space are suggested. For example, we can try lowering the lambda for cycle consistency loss so that the model puts more emphasis on cartoon style translation than on the input information retention. In addition, we should also learn more about cartoon GAN itself. And then we can see if a complete cartoon GAN, including the process of pre-training the generators, can easily translate real people to Simpson cartoon images. And another direction we can go is to increase the number of data points in a data set. Of course, that will require more resources for sure. As the state-of-art public available image generation tool, Stable Diffusion may give us a better result. However, it's more complicated and it should be harder to customize and to train. Thank you very much.